Welcome. I decided to do 2 introductory lectures before I go on into the implementation challenge. That's just because that way I can be more straightforward in the actual implementation. So in this lecture I will cover basics of classical mechanics. And we will start from the action principle, go into the Hamiltonian mechanics, Poisson brackets and symplectic propagators. But first, as a catch, I will quickly code few propagators into the harmonic oscillator and a little bit hand-wavingly analyze their stability, and sort of that will be a justification of why one should be interested in this. So we of course have harmonic oscillator, which has some position and some momentum. I will call the position Q and the momentum P. So this vector Z will represent now some position and momentum of it. So it's a 1 point in the phase space. And then I can write the total energy. The total energy in the case of harmonic oscillator, it's a quadratic function of the Q and P. So it's something Q squared and something P squared, and it could contain something Q multiplied with P as such, but it doesn't. So if I define a matrix H where it has it looks something like this. So let's have the mass 0 and a frequency 0. So now this function here will actually end up being, so you can see that the Q is here in the first column of Z. So you will have that the total energy of the system will actually look like this, and then like this. So this is just the total energy of the harmonic oscillator. Then I will define a symplectic matrix, which will look like this. And then I can take so if I take the derivative of E with respect to Q or P, I can actually do that by, it will actually become just H multiplied by Z times 2. So I can actually do something like H times Z, and then the Hamiltonian equations of motion, you have like d E dq, so we have dp, so dot p equals this one, and then like so, and then dot q equals d e dp roughly. So I can multiply this with the matrix, so I can code the propagator in such way that we have some time step, and we will update the position of the in phase space by finite difference approximating this Hamiltonian equation, and we can do it over 1000 time steps, and we can store the trajectory, and so let's see what it looks like now. We see some solution to harmonic oscillator. Let's solve it a little bit longer, and let's little bit I increase the time step, and we can see that this propagator is not stable. So this is the oscillation of the harmonic oscillator will be getting out of hand, and we can then let's split this Hamiltonian into 2 parts. So first part will have only momentum and the dependent terms, and the second part will have only potential. So now sum of H1 and H2 equals to H. So now, for example, I can code a propagator where I propagate like this in the first with respect to H1. So I first half step with H1, then full step with H2, and then half step with H1. So in total, to first order it corresponds just multiplying with the H and J. But in the end, it will be much more stable, so you can see that the propagator is stable. And let's just increase the time step even more. And you can see that it's still stable. So it's stable even, there's just few steps in the full oscillation of the harmonic oscillator. So this is a symplectic propagator. It's some sort of Verlet propagator. And that's what we are gonna find out